to the session. And we start with quite interesting lecture by Professor Sergey Sharapov from the Mogilev Institute in Ukraine, from this institute. And he will talk about Sagnac. I believe that on Monday and on Tuesday have listened already presented some lectures where phase measurement, phase estimation have been mentioned here, and also Sagnac interferometer and optics have been measured. Today you will listen lecture about what is Sagnac. I believe it's some interesting and useful application, and a couple of words about Professor Sharapov. He has graduated from the Strasbourg University in Kyiv in 1992, and in 1996 he got his PhD here in Mogilev Institute, and Doctor of Science also here in degree in 2010. He has made a lot of experience, a lot of postdoc position, for example, in the University of Pretoria in South Africa, in Switzerland, in the Newcastle University, yes, in Italy, in Turin University, in Canada, in Newcastle University, and starting from 2011, he is working here as a leader of laboratory. Yeah. So Sergey is a well-known expert, is an exceptional expert in the field of condensed matter physics and solid-state physics. He is one of the most cited scientists in Ukraine. In particular, he is well known by his contribution to physics for graphene and lecture Nobel Prize in 2008, I believe. Yeah.
Maybe 10, but it will be in my transparency.
Maybe 10, yeah. Nobel Prize when Andrei Gem and Novoselov, yeah, they obtained Nobel Prize for graphene, and they have cited work by Professor Sharapov. So today we have listened one work which is related to Sagnac effect, also in the graphene, not only for optical fields, but for photomaterial fields. And further you can think how to apply it to quantum metrological tasks, maybe. So, Sergey, the microphone is yours.
So thank you very much for nice introduction. And well, actually, I am not a Sagnac effect person. And I learned about the existence of this effect a couple of years ago, but actually exactly due to my interest in graphene. And so I put in the title of my talk that it's not just about Sagnac effect, but Sagnac effect in graphene. And I will actually try to do three things in my talk: to introduce main things about the Sagnac effect, and because actually even in I would say that in the lectures which I heard where this effect was mentioned, I already felt uneasy that there is some misunderstanding about this interpretation. And some research work that we published, I will talk about at the end of my presentation. And also you will see I will also advertise a popular article that I recently published about this effect. So the outline of my talk is the following: that I will explain what is the essence of this effect and describe its brief history, try to explain you, and also you already in the lecture saw some expressions about this phase shift in the Sagnac effect. I will introduce main known expressions. Then I will switch to, actually we also heard in the talk that Sagnac effect is especially interesting in quantum metrology when it's observed for massive particles. Then I will actually switch to observation Sagnac effect in solids, and because there are very few of them, I will go to another interference effect, which is quite well studied in solid-state physics, especially in graphene, introduce Aronov-Bohm effect, maybe heard. Then discuss solid-state proposals of the Sagnac gyroscope on graphene, Then actually I will switch to discussion of graphene, and actually I will try to provide you the simplest, which I know, derivation of the general Sagnac effect and discuss it specific in graphene. And I will present the results of our work, discuss actually what is quite relevant for our present life, military applications of this effect. And you see that I'm going to try to put it in 1 hour. So I put some formal stuff if I have time, and if you ask questions, if I manage, I will also have it after the end of my talk. So what is the Sagnac effect? Sagnac effect was discovered in 1913. And actually, yesterday when I was trying to make my presentation more popular, I looked on the web photos and found the way how at this time Sagnac was teaching. So this is probably the resolution is not very good, but there are 2 assistants and professors. This is the way how lectures were presented at that time. So what is the essence of the Sagnac effect? We have some rotating platform, and we have source of, in the case of Sagnac, original work, light. And we send light in the opposite directions around this rotating platform. In practice, if we speak about light, of course, now we have optical fibers, but in Sagnac case, he put some mirrors. So it was more like triangular, square shape, but actually it does not really matter. And if this platform is rotating, they meet at the detector, which is at the place of the source, so full circle one direction, full another. And Sagnac effect consists in the angular frequency dependent phase shift between the arrived waves. And here in this equation, gamma is this relativistic factor. This is radius of the platform, angular frequency, and you realize that the rotation speed is very small. So in all practical applications, people ignore it. And here, what's important is omega small is the frequency of the wave. In the case of Sagnac, he used it just the frequency of light. Actually, if you look deeply at the history of the effect, more deeply you discover that a couple of other scientists were also proposing some of this kind of experiments, doing it, but as usually only one name is left in the history, and in the literature is called it the Sagnac effect. And how to explain the Sagnac effect? In my talk, I put all possible reference. So if you are interested, you may just take, and I can share with you the presentation, and you can use it. So this is very comprehensive review which I found. And normally, the simplest explanation which I found in this review, if you use Voloshin addition formula from the special relativity. So you have phase velocity. Actually, the derivation is not only for light, it's for any wave with a phase velocity v phase. And you have on rotating platform, phase velocity changes depending if wave goes in the opposite direction to rotation or in the same rotation. This is plus minus. And obviously, you see that if I put the velocity of light, the velocity would not change, obviously. So it will remain c. This is a special relativity. And you have, during the time of rotation, the path that wave goes increases with respect to circumference of the circle. So you have this change. And the time that take for the wave to pass is t plus minus, is this L plus minus divided by V plus minus. And you can do this rather simple algebra and find different times it takes for the wave to reach the detector. So this is the expression. And if you count the time difference between the necessary for the wave to arrive, you discover this expression, which is very interesting, that phase velocity in this expression disappears. So it's proportional to the area of this interferometer, angular velocity, and this is what I did not say. The T prime is the time on in the frame on the platform. That in the frame moving with the platform, this is unprimed frame, you divide this T prime by this relativistic factor gamma. And if you want to count, to calculate the phase shift, or in English it's called phase fringe, between the two waves, you multiply it by the frequency of light. And this is the way how you derive this expression. Okay? Any questions? This is really the simplest derivation which I found in the literature. So a little bit about history of this effect, and I don't know, it's actually, let me do the experiment. How many of you heard about this effect before? Okay, so just two.
Out of here.
Okay, that actually I have at least my own hypothesis why it's not known to wide audience, because it's anti-pedagogical effect. I will explain why. So maybe you heard about this philosopher Ernst Mach, that he criticized the concept of absolute space by Newton, published his book in 1893. That and actually George Sagnac also was on the opposite wave, and he was thinking still about existence of motionless mechanical SR. And many ideas of Mach inspired Einstein to create his special relativity, 1905. And Sagnac effect, he discovered it in 1913. And for Sagnac, actually, this effect was a proof that FR exists. And I heard that some of you complained that you don't have problems in these lectures. And I propose you some childish problem. Forget about special relativity, since that for light you can use Galilean addition formula for velocities, and try to derive this phase shift for Sagnac effect. And the surprise will be that you will derive the correct result. And this is, I believe, this is the reason that the problem with the Sagnac effect, that because it can be derived standing on the opposite concepts. So you can think about existence of FR or special relativity, you will get in the first order the same result. So the effect itself cannot be used to prove this special relativity theory. And this is probably the reason why it's not appears in the usual most of the textbooks. I will tell you later about. And another thing why probably this his name was not very welcome is that 1919 he received a prize for the experiment that's a rebuttal of relativity principle, constancy of light, and reality of absolute space and time, actually. And actually, people were asking whether it's possible to explain Sagnac effect in the special or general relativity, and the proof is done by Langevin in 1921. And actually, yesterday I was reading some historical article. There is another physicist, Kaluza. He did it even earlier. And von Laue did the proof in the special relativity. And actually, look in the literature, I discovered that things about, that special relativity, at least the way how Einstein considered it, it's about clocks, synchronization of clocks, etc. Да? And this is, I found that in the literature, people are still discussing what happens if you consider rotating platform, how you do this clock synchronization. So, and it's actually pretty interesting to read that people are still discussing it. Okay. Now I introduce you another derivation of the Sagnac effect. Actually, it goes to Landau-Lifshitz, volume 2. And what's interesting that in Landau-Lifshitz, this derivation of Sagnac effect is actually present, but name of Sagnac is not mentioned at all. And probably I don't know why, but maybe one of the reasons that this history that he was not was not considered as supporter of special and general relativity. And another derivation, it's actually basically the same, but name of Sagnac is mentioned. I advertise this Louis Ryder textbook on general relativity. So basically, this derivation goes to the way how you, from early school, you studied what is it rotation. And this is how you interpret, how you treat rotation using in terms of the special relativity. So in primate coordinate system, you have this relativistic interval ds square, which is standard, so that primate is the rest frame, and non-primate is rotating. And you do essentially the Galilean transformation to the rotating frame. This is a standard transformation, probably you recognize it. And in this rotating frame, you have this metric, appear non-diagonal components. And what's interesting that in this rotating frame, you have non-diagonal term of the metric tensor. And interpretations are getting a little bit tricky. And the thing that if you try to do this clock synchronization, which I mentioned, that if you go around circle, you obtain this difference of in time proportional to this non-diagonal component of the metric tensor. And this is how you, this is how you derive this delta t. Okay. Now I go to presenting you main expressions for the Sagnac effect. So that I started with the expression where I had frequency of light. Now I put using already quantum physics, I use that frequency energy of light is proportional to a Planck constant multiplied by frequency of light. And so this is the way how I come back to the previous expression. And as I said already, I would ignore this gamma factor. It's small. And for light, if I substitute relationship between the light wavelength and frequency, I obtain this expression. This is in the lecture you heard on Tuesday, you had a similar expression where you had, even in more generic form, you had wavelength, but here you had even arbitrary velocity. And I claim that this expression is actually very misleading. And it puts you to some wrong interpretation of the Sagnac effect. And okay, this is for light. What would happen if I consider slow massive particles, like atoms, that you were discussed, it's Sagnac effect observed for atoms. If I use Einstein formula, energy is mc square, I would obtain this expression for the Sagnac effect. Okay? This is the basic expression used when Sagnac effect is realized for massive particles. And here, actually, can I rewrite this expression in terms of the some wavelength? Yes, I can, but not de Broglie wavelength. But have you heard what is it Compton wavelength of electron? So this is the way. This is if you have photon of the which has the rest and which energy is coincides with the rest energy of an electron, and calculate what would be the wavelength of this light. This is the way how you define Compton wavelength. So in this case, this equation is would be correct, but it's wrong to think that this lambda is the de Broglie wavelength, which is which appears more in non-relativistic consideration. And what's interesting, let's compare the phase shift for photons described by this equation, and for atoms or electrons, if we use interferometers with the same area and which rotate with the same angular frequency. So you will see that it will be the following enhancement factor: mc squared divided by the energy of light. And if I use for atoms, it 10 in power 10, and yesterday I saw that actually for rubidium it's even 10 power 11. And for electrons, it's in 10 in power 6. And this is basically the main reason why experimentalists that talk about Sagnac effect are so excited about Sagnac effect realization using material particles. This is the reason why in this lecture about cold atoms, you heard that it's very interesting to study, to realize effect in cold atoms, and it was of both. So for light, obviously, you don't have to cool the system down. For light, it's very easy. You use modern lasers, you use fibers, and I will show you photos of some real devices. But why should you bother to cool down atoms to nano or millikelvins to do Sagnac effect? The reason is this enhancement factor. And some overview of experiments. Sagnac effect indeed for electron waves was electron waves in vacuum in 1993, for neutrons 1979, and for atoms first observation is 1991, and actually a very recent article I heard is from 2022. You see, this is the temperature. Actually, not nanokelvin, millikelvin, and area of interferometer 11 square centimeters. And what's interesting that, at least in the article, maybe it's advertisement, maybe not, they use this to detect rotation of Earth. But they discuss whether it's possible to detect some extraterrestrial rotations. So rotation of Earth around the sun and so on. And in solid state devices, I am aware of only one article from 1965 when Sagnac effect was realized in superconductors. And to the best of my knowledge, this goes to the vacuum observations. And Sagnac effect in solids was not observed. And I did not find it in the literature. So now I slightly switch the direction of my talk and would talk to so-called Aharonov-Bohm interferometry. So what other interferential effects, which kind of other estimation of phase is done in solid state physics? And although I am a theoretician, I will try to share with you my excitement about interesting experiments. So let me give you some brief explanation about kind of interferometers which are available. First one is Mach-Zehnder interferometer. You already actually saw this in the lecture. This is the first type, and Aronoff-Bohm oscillations and quantum Hall effect H channels are in solid state are realized on this interferometer. I was not lazy to check. It's actually Mach is the son of philosopher with whom I started my talk. Another interferometer is Fabry-Perot, and the third kind of interferometer is called Sagnac interferometer. You see that you have beams of material particles or light are doing full circles. And actually, Sagnac interferometer is the best because it's the most efficient as compared to Mach-Zehnder. Because you see that here the path is only half circle or half square, and here is a full, and this affects the effects you saw are proportional to the area of interferometers, and obviously Sagnac would be the best, but in practice in solid state we can do Mach-Zehnder. And now, as I say, I switch to Aronoff-Bohm effect. Have you heard about in quantum mechanics?
Yeah.
How many of you? Okay, it's actually very good that you will hear about. First of all, I advertise one of the best descriptions, of course, in Feynman's lectures in physics. The effect, although quantum mechanics was created 100 years ago, the effect was picked up and realized only in 1959 by Aronoff and Bohm. So what we have? We have the source of electrons and have this famous double slit experiment. In quantum mechanics, you heard about. This is basic interference experiment, actually goes back to Young experiment in optics, how the wave nature of light was proven. And the only modification, let's put inside the solenoid with, which produces some magnetic flux. And what's very exciting about Aronoff-Bohm effect, and as I discussed it with some physicists, do not completely understood until now. The question is the following: if I put source with magnetic flux here, and magnetic field is only present in this circle, and here is outside of the circle where electrons go, only vector potential is present. So how do you think works, would it affect the interference or not? In classical mechanics, you know that particle in magnetic field, Lorentz force, is related to the magnetic field, okay? Here I claim that no magnetic field and there is a vector potential. But still, this is what's pointed out, that vector potential causes the shift of interference picture. This is basically this phase fringe, if you wish. And shift in Aronoff-Bohm effect is actually still proportional not to the vector potential, but due to the Stokes theorem, is proportional to the magnetic flux and field. So still physical answer depends only on magnetic field, but you have action of magnetic, I cannot say even magnetic field, but you have action of something on electrons in the regions when magnetic field is absent. This is the Aronoff-Bohm effect. And actually, I put some experiment from article 2023, which is done on chemical vapor deposited graphene. Well, it's a long story to discuss what is its CVD graphene, but this is the biggest samples of graphene which are produced by now, which are the size of like TV screens. And they essentially what this is the scanning electron microscope photograph. And this is the scheme of the experiment. So you have a ring made from graphene, and you send current through this ring, and you apply magnetic field. And this is how modern realization of the Aronoff-Bohm experiment. And as I told you, why I switched to Aronoff-Bohm experiments, the reason is because there are no observation of Sagnac effect on these devices, but there is plenty of beautiful works, experimental, modern. First work actually observed on electrons in vacuum in 1960, but this business with observation of Aronoff-Bohm effect continues until now. And a couple of more experiments I will discuss. Have you heard about carbon nanotubes? Actually, they were created even long before graphene. And this is one of this is I showed you nanotube because probably here in this picture from an experimental article you will not recognize it. And this is suspended nanotube. I put, you see how small it is, diameter less than 2 nanometers. It's quite long, it's suspended. And you create gated structure, so you can change the carrier density in it, and you send magnetic field almost parallel to this carbon nanotube. So this is the simplest realization of this Aronoff-Bohm effect. And indeed, in this experiment, Aronoff-Bohm effect was observed. If I go to graphene, more modern publications, you can create this rings for observation of Aronoff-Bohm effect, but flat geometry of graphene allows you to put more gates, and actually what's interesting, you can put gates to control carrier density in graphene samples in the arms of this interferometer. And actually what's really beautiful, this is the experiment done on bilayer graphene. In one part of the ring you have carriers holes, and another one you have electrons. So this is what's shown, what is filled. I will later explain. And still you observe Aronoff-Bohm oscillation in this system, and you see that Aronoff-Bohm oscillations are not affected in this bipolar regime, but this shows you, well, this modern experiment advancement in these systems. Finally, the last experiment that I can show you that up to now, all I showed you, those rings were done on real graphene. So I mean that like modern chips are produced. So you use the same technology, you create this rings in graphene. You chemically remove conducting areas, you have rings. And what's here? Here you have, sorry, here it was actually monolayer graphene. I mixed it up since. And here you put bilayer graphene, and you have full small flake of graphene. And how you create ring? You put on top metallic gate. So that physically you don't create ring from conductor, but you change voltage on this ring gate, and you create conducting area in graphene. And this is, you see how this thing work. And why graphene? In all this science, you probably realize that the main enemy of interference effect is keeping coherence of the waves. And if you have particles in vacuum, phase coherence is probably relatively easily to keep, although in gain. In cold atoms, you saw that how difficult to cool down atoms so the wave functions will be coherent. So here's the size that mean free path is 15 micrometers, and so the coherence is of electrons is observed over the ring, and temperature is 300 microkelvin, and so on. And if you analyze this Aharonov-Bohm oscillations, you have if you change flux through the ring, there is a periodicity in the flux with the period of flux quantum. And this is some experimental data, and you see, if you do Fourier analysis, you see periods of oscillations, and you see that I have one flux quantum, two flux quantum, and so on. The reason for this is the number of rotations that electron makes around the ring. So this is how it works. And why I started to tell all this, that for Sagnac effect, and I will, at the end of my talk, show a couple of references. Propose, this is just a patent at this stage. Propose to use the array of the rings, and again, send current through the rings, and realize Sagnac effect in the solid state devices. This is what is proposed in the modern literature. And now I try to derive for users, present the derivation of Sagnac effect for massive particles from the wave equation. And have you seen this kind of equation before? This is called Klein-Gordon-Fock equation. And since I heard that in the first lecture you were talking about Schrödinger equation, I will remind you some interesting historical fact. Actually, it's probably correct to call it also Schrödinger equation, because Schrödinger, when he was trying to create quantum mechanics, actually, everyone at this moment already knew theory of relativity. He wrote down actually exactly this equation. The problem was that when he tried to calculate spectrum of the hydrogen atom, he did not get the correct result. So this only remained in some correspondence with other scientists, but actually this equation is also belongs to Schrödinger. And so this equation is the equation for scalar particle of mass m, relativistically invariant equation. And here, firstly, I wrote in more generic form in coordinate system with arbitrary metric tensor, and this is in the inertial rest frame. And now let me try to solve this equation in the rotating frame for the ring. And I consider, again, and in this first slides which I showed you, I send waves over the ring in two opposite directions. And if I want to switch to the rotating frame, I should do this coordinate transformation. This is what you would do in the classical mechanics. And if I use this, if I solve this equation in the rotating frame, it's trivial algebra to derive the corresponding equation and to see that this solution satisfies this equation in the rotating frame. This is actually, I follow this article from 1990. And for me, this is actually the most, I would say that, although I say that first derivation of Sagnac effect is the most simple, but for me, if I think about applying this equation for material particles, this is for me the most simple way to derive it. Okay, so this is the phase, and if you see, I have in the rotating frames, the dispersion law is this. Okay, I have two signals counterpropagating start at the phase 0, and then put here phase 2 pi and minus 2 pi and find the difference in the phases. Okay? And this is, you see that I would get the Sagnac effect. And if I cross out the mass, and of course, I would instead of Klein-Gordon equation, I should solve in principle Maxwell equation for vector particle. But the principle is the same. That for massless particle, I would come back with the Sagnac effect which I had before, and for massive particle, slow massive particle, I put instead of omega. I neglect this term comparing to the rest mass term. I would obtain this non-relativistic limit of this and this expression for the phase shift for the Sagnac effect. And you see that this is the reason why I consider this expression for Sagnac effect as the most basic and explaining physics of the Sagnac effect for massive particles. And you see also what's actually probably difficult to realize if you think about Sagnac effect. This effect is intrinsically relativistic effect, okay? But because mc square and this formula remembers about its relativistic origin. And if I put mc square, then c disappears, and you're attempting to think that this is some kind of non-relativistic effect, which is not. And okay, here is something, I don't know, maybe complicated, maybe not, but this also goes back to the lecture where Andrei Semenov told you that in quantum physics, states are not vectors in Hilbert space, but rays. It was something. So let me, in special relativity theory, the phase is the relativistic invariant. This is a scalar. And let me do non-relativistic expansion of the phase. Okay? This is standard way how you derive non-relativistic limit. Then if I go to, if I use Lorentz transformation, I go to the moving coordinate system, I would get, so this is this non-relativistic phase. In addition to these terms, I would also get this. Okay. And so this is actually goes back to another interesting thing that you probably, when you had the derivation of Schrödinger equation, heard that it's derived from the principle of Galilei invariance. Yeah? And if you look, there are modern textbooks that explain this in detail. If you look Landau-Lifshitz, there is a simple problem. How wave function transforms under the Galilean transformation. So that under Galilean transformation, phase transforms also by these terms. And if the implication of this for Sagnac experiment, again, if I use these signals going in the opposite direction, this is how I would get from Schrödinger equation derivation of the Sagnac effect for massive particle. But you should realize the following: that in Schrödinger, so this transformation of the phase in non-relativistic quantum mechanics actually emerges from relativistic theory. So this is the remnant of this transformation is actually, as you saw here, appears from the relativistic transformation. And so that this does not contradict the statement which I made, the Sagnac effect is intrinsically relativistic. And actually, this expression for Sagnac effect, you can also read in terms of so-called de Broglie frequency. So that instead of the de Broglie wavelength, de Broglie also introduced a de Broglie frequency, This is the frequency with which oscillates any particle. So mc squared divided by Planck constant. And there is also something interesting that in quantum mechanics, in non-relativistic, you normally think about de Broglie wavelengths where it's h bar divided the non-relativistic momentum, yeah? What is the de Broglie wavelength? But again, if you look carefully at quantum mechanics textbook, actually, original derivation of de Broglie was relied on relativistic approach. De Broglie actually firstly considered particle in the rest frame, so it's not moving, but it oscillates with this de Broglie frequency, and then did the corresponding transformation. So that I would so this is the way how you can express Sagnac effect in terms of this frequency. Okay, now I think I'm actually in time that. This is something about graphene. Have you heard about graphene and basic physical properties of electrons in graphene? In solid state physics, the standard thing that happens that dispersion law of electrons is approximately parabolic, but effective mass changes. For graphene, this is not the case. For graphene, the dispersion law of electrons is like for light. So linear. And this is this is what Andrei mentioned. I forgot. So this Nobel Prize in 2010 for discovery of graphene. So the property of graphene is that the particles in graphene are massless, and this is what came to our problems that we decided to study. That I just so in all previous talk I put two different lines. I was talking about photons saying they are massless, and I was talking about massive particles. And I just told you that effective mass of electrons in graphene is 0. So how should I think about Sagnac effect in graphene? Is it like for photons, or it's like for massive particles? This is. Okay. Actually, this is what I was thinking originally, and actually here in these interferometers which I showed you, people when speak about Sagnac effect in solid state, they put exactly this m effective mass. So for Sagnac, so those authors in the articles put in the Sagnac effect, they put this mass. And this was also forced me originally think that this is that for graphene is like for photons. Actually, the thing that we found that this is not. In this derivation of the Sagnac effect in Klein-Gordon equation, sorry, you saw that electrons have this electron time dependence has this quickly oscillating factor related to the rest mass. And normally in solid state physics, we think that point from which we count the energy is an arbitrary point. But the statement that in our work we did is that actually for relativistic approach, it's important to include the rest mass of particles. So the statement is the following: effective mass does not enter the Sagnac effect. Sagnac effect is related to the true mass. This is basically what we did in this article, and we repeated this calculation. And essentially, our statement that for graphene, the Sagnac effect will be determined by the rest mass. Okay, and I have a couple of minutes for questions and to entertain you. But actually, what's interesting that Sagnac, after he discovered his effect, he proposed to use his effect for ship navigation. It's 1914. And only development of modern physics, creation of lasers allowed to utilize Sagnac effect. And this is I found review from 1997 where this unlikely equation for Sagnac effect with velocity and wavelength appears, which I don't regard as very good. And actually, I put a lot of text from this review, this you can read, but probably from news about war in Ukraine, you heard that as a present from our Western allies, we get this GDEM. Heard this abbreviation? How many of you? Actually, more than about Sagnac effect and other things. And the thing that this is basically the piece of equipment based on the Sagnac effect, which allows to bombs, missiles to go to the target even when GPS signal is lost. Because it provides very precise navigation. So everything is actually, all this equipment is based on the Sagnac effect. And my point of view is that now, maybe not, mostly not physicists know about the Sagnac effect, but mostly engineers, actually. Except to the physicists who do this very neat experiment and called atomic gases or something. And those basically first Gulf War when this weapon was produced. And here this is a picture of gyroscope produced by Arsenal factory in Kiev. Don't be afraid, I did not steal the secret. Unfortunately, if you look Wikipedia, you discover that this photo is taken in some military exhibition held in Russia in 2011. Okay, this ring gyroscope is not is based on the Sagnac effect, but engineering is different. So they, instead of measuring phase fringe, they put different frequencies of light and study and obtain some beatings. And something which I told you that I look at the titles of the article. One of the experiments which I showed you, this observation of iron bomb oscillations on CVD grown graphene. An affiliation, one of the authors is this one. And another abstract which I found, design a numerical simulation of quantum graphene gyroscope, also goes to some military lab. And I did you more introduction about Sagnac effect by my own scientific result is that Sagnac effect in graphene is still governed by the free electron mass up to the binding energy in graphene. And I hope that this title which I showed you and this experiment on our of bomb promise that it will be observed in solid state devices. Also to advertise Kiev Academical University, I should actually explain you that first author of this article, which I told you that I will present, is our master student who will defend, I hope this year, his diploma in his already article in Phys Review B. And also, I am the author of a popular article, maybe also interesting. Have you heard about Kunst journal? How many of you? Not too many, but actually it's very nice modern Ukrainian scientific popular journal, which publishes vast majority of articles in all popular domains. So thank you for attention.
Thank you very much. Thank you very much for this nice talk, for this nice lecture. So I believe we have lectures. So lecture questions from local audience. Yeah. Please.
Thank you for your talk. It was really interesting. I'm just curious about the slide that you showed about the derivation of the Sagnac effect from the general relativity point of view. I'm not sure I get where the general relativity component comes from, because the space-time is still flat. You just transfer to the rotating coordinate system, and that's why the metric is no longer Minkowski, but there is no curvature, so it's still special relativity.
Yes, indeed. This metric tensor does not have curvature, but somehow when you well, I would say that already non-diagonal form of metric tensor is already more discussed in general relativity in this sense. At least the positioning of this derivation in the corresponding textbooks already corresponds to the general relativity. And this goes back to the original work by Langevin. It's also considered as a general relativity explanation. In principle, the sense that in any case, rotating frame is not inertial. So in any case, you like in general relativity, you go to inertial frame on each separate point of the circle. So in this sense, you may question how the special relativity derivation, whether it's correct or not in this respect. So
okay, thank you.
Thank you. More questions? Anton, maybe questions from online?
Yes. We have
Yeah,
actually a lot of questions from online.
Yeah.
So the first question is slides page 7. On the page 7, already I see massive particles, non-relativistic case. Then why is one prohibited from using the de Broglie wavelength? Why the need to adhere to Compton wavelength?
Okay, well, at least I would put it like this. Since I already derived it myself from Klein-Gordon equation, I believe that this form is the correct one. If you think that this is a de Broglie wavelength, you would get the wrong result. And actually, my own way of understanding Sagnac effect was also that in one of the review article, I found this expression with, like in this talk on Tuesday, with the velocity in the dominator multiplied by the wavelength, and I believe that it's rather misleading. So this is one of the subtleties of the Sagnac effect which I learned, but at least I would put it like this. Since in Klein-Gordon equation I did all algebra, I believe that this is exactly Compton wavelength and nothing else. Part of the problem is that community studying Sagnac effect is very different. Some people from cosmology, from general relativity, and they do not do mistakes. And some people are coming basically from engineering, and this kind of not very critical usage of the formulas, in my opinion, leads to basically to mistakes.
Yeah, but it's in principle better interdisciplinary. Topic, and
yes,
this is why.
But I mean, part of the problem is that for engineer people or people coming from other area, they just take this equation as granted and then start to deviate from the correct interpretations.
Which lambda equation, I mean, because people online don't see your laser pointer. Yeah. Yeah. Okay, Anton, other question?
So another question is the what is the major differentiating points from Sagnac interferometer to Mach-Zehnder one, and how does like Sagnac interferometer works?
Well, basically the way how you set up the path, that this Sagnac interferometer is actually is the most efficient compared to Mach-Zehnder is factor 4, if I'm not mistaken. And the question is how you can do Sagnac interferometer on material.
Okay.
Okay,
Anton?
so the next question is, can you introduce a reference in which one might follow the relativistic origin of the broiled chain of thought more for wavelength form or more closely? I had heard about it, but I haven't found something concrete.
I think there is a translation of Max Born, the same who also was mentioned in the first lecture, Atomic Physics or something. There is a old Russian translation of this book. Actually,
But not also maybe original. This is original book maybe. Max Born book, yeah?
there is Max Born book on atomic physics, and it's translated into Russian in, I don't know, 50s, 60s, and it's...
No, but original book Max Born, yeah?
Yes.
Because it's translated, it's another interesting class.
No, but I mean, you can probably hardly find it, and this scanned version. If you contact me, I can also there are some reviews on this stuff. So if you contact me, I can provide you with a couple of references. Sorry.
You can send me, for instance, the references by the email or to Andriy, and then I'll just share all the references to the by the email.
Okay, just to get in the contact, do you know my email? It's in the I registered, so
no, but we can share this.
Yeah.
Also, we can use WhatsApp chat for this,
Yes.
and WhatsApp, you can simply share in WhatsApp.
Okay.
Okay, Anton, next.
Yeah, the last question. Is it true that SE as well as twin paradox are basically the same things? Both are connected with non-inertial frame and path-dependent time, non-holonomic difference.
Actually, I already feel that my knowledge of relativity is not sufficient. Twin paradox, probably not. Twin paradox is that at some point you go to the accelerated frame. But I strongly advise, if you want to understand better physics, is look first chapter of this again this Lewis Ryder textbook, because it's I think it's like neighboring pages. First the twin paradox and with the acceleration you solve, and then in a couple of pages you have the Sagnac effect explanation. But the word non-holonomic, that you cannot return to the to the same point for Sagnac effect, I think is the correct one.
Okay, Anton.
Okay, I think that's it. We don't
No,
have
we are not ready. We have questions still. Yeah. Okay.
It's related to the question about the history of de Broglie coming up with all that stuff. There's actually a really nice series of videos on YouTube about history of quantum mechanics, which covers that stuff and shows how de Broglie it goes through the papers and shows how de Broglie
basically used relativistic reasoning to get to that stuff. I'll share it on WhatsApp.
Wow, well, great, thank you.
Yeah. Thank you. Another question? Yeah.
Yeah, thank you for your lecture. Can you please once more explain about this part with carbon nanotubes, where what gives a rise to Sagnac effect and how this leads to the...
No, in this experiment,
sorry.
effect.
Oh, okay. Sorry.
So this the thing that I would say that even the toy mathematical problem. If you think that if you have carbon nanotube, it's already ideal. It's already tube for realization of Aharonov-Bohm effect.
Okay.
So if you send you apply in the experiment, you apply magnetic field parallel to the axis. And they use this gate to change the carrier density in the nanotube. And there are two contacts. So you send current in the vertical direction. And then what you observe that your conductivity is oscillating. So basically even in this setup, the only thing that you can it goes back to this estimation theory that you observe that your current is oscillating as a function of magnetic flux, for example. I don't already precisely remember whether they changed magnetic field or voltage, but you observe the oscillation, and the period of oscillation is proportional to the flux.
Okay, thank you.
Okay, more questions? It seems that not, Anton.
Yeah, no more questions.
Okay, then let's thank our speaker again. At the moment, we have coffee break for 20 minutes, and after that, we will have a new lecture about atom
Actually, less. We have